Hello folks, this is 2024 October-November paper 4-2 and the question number is 5. This question is concerned with the chapter oscillations, or we can say simple harmonic motion. It says figure 5.1 shows a pendulum consisting of a metal sphere suspended by a thin string. The sphere undergoes small oscillations about its equilibrium position, which means it is more likely to have simple harmonic motion. The oscillations may be considered equation harmony, yes, considered. Figure 5.2 shows the variation with time t of the displacement x of the sphere from its equilibrium position. It means the equilibrium position will be somewhere around here, so it's the displacement. On figure 5.1, draw an arrow from the center of the sphere to represent the direction of the resultant force acting on the sphere when it is in the position shown. So we have to draw the direction of the resultant force. So it should be when a body is in SHM, the force will be opposite to the displacement. The force will be directed opposite to that of the displacement. So this is the displacement, so the force should be like this. The force should be like this. Like this. And the direction of the force should be perpendicular to this thing. So this is the direction of the force experienced, like this. Now in the next page we have okay, it says the mass of the sphere is 0.15 kg, so it is a small m here. State the amplitude of the oscillations. We have to state the amplitude of the oscillation. It is not to be derived but stated. So to state that, I again have to go through the graph here. So let me fold this paper. So this is the graph. So in the graph, what we have is this is x, and the maximum x is here. So this is 0.01, 0.02. So this thing should be 0.015. 0.015. So then the one next is 0.016. So it should be 0.016 meters. Now determine the angular frequency of the oscillation. So simply we have omega is equal to 2 pi by t, but we have to find t from the graph itself. So in this graph, what we have is from this top to this top, we have the time equal to 0.4 seconds. 4 seconds. Or I can say from this bottom to this bottom, it is 0.2, it is 0.6. The difference is 0.4 seconds. So that's why this t is equal to 0.4 seconds. So it should be 2 pi by 0.4 equal to, so when I do calculation, it will be 2 into shift to pi divided 0.4 is equal to, so 15.707 and so on. So it is 15.707963 and so on. So when I make a shortcut, it becomes 15.7 radians per second. Now calculate the total energy of the oscillation. So E total will be equal to 1 by 2 m omega square and x naught square. X naught is the amplitude. So it's equal to 1 by 2 into m is this 0.15 into omega is this is, so it is 15.7 squared into x naught is this, it is 0.016 squared. So it becomes, so I have already have this 15.7 here, it is squared into 0.016 squared into 0.15 divided 2. So it is 4.73741 and so on into 10 to the power minus 3 joules. So in shortcut, it will be equal to 4.74 into 10 to the power minus 3 joules. Now, yeah, sketch the variation with x of the kinetic energy Ek of the sphere. So we have to draw a graph of the kinetic energy of the sphere with respect to x. So what we have to remember is during this oscillation, what we have is it oscillates like this, somewhere like this. So at the edge, the value of KE should be equal to 0, or I say EK is equal to 0. And here also, this EK is equal to 0. So this occurs at a displacement of this 0.016. So at 0.016, EK should be 0, 0. So at 0.016, EK should be 0, 0, 0, 0. And the maximum value is this much. So it should be at x naught or x equal to 0, the max value is this. So it should be, this is 5. This is 5. This should be 4.5. 4.6, 4.7. So somewhere around here. Somewhere around here. So this is 4. This is 5. 4.6, 4.7. So somewhere around here, this should be maximum. So maximum, then it is 0 and 0. Now the graph should be a parabolic graph. The graph should be parabolic. It's because K is equal to EK is equal to 1 by 2 mv squared, and this is 1 by 2 m. V square should be omega square x naught square minus x square. So when I break it up, it will be equal to 1 by 2 m omega square x naught square minus 1 by 2 m square x square. So here we have the graph of x and EK. So in front, in x, we have got x square and this. So x square means parabola and minus means reverse parabola. So this graph should be a parabolic graph. So top here, 0 here, and parabolic. So it should be somewhat like this. It should be symmetrical actually. From here, here, and here, it should be symmetrical. So my graph should be something like this. And then I'll try to make this as symmetrical as possible. And I don't have the luxury of eraser, so I can't rub it. I have to make it in one go. So yeah, so this should be the almost correct graph for this stuff. So a reverse parabola. Okay, this is the answer to this question.